Right, so we started on chapter 2 last time, and we started talking about the general structure of this Hamiltonian, where you have a device part connected to the semi-infinite lead part. And the device part is this little 3 by 3, and that's the part you need to calculate. This GDD over here, that's what you need, the 3 by 3 part, and you've got this infinite part. We just included the left lead to keep things compact. And you have to do something to get rid of that semi-infinite part. And the only place that the lead part couples to the device part are these two elements right here, the way we set this up in our, because we're always going to write the Hamiltonian in a way that is block tridiagonal. You all know what block tridiagonal means. Give me an affirmative. Block tridiagonal. No. Okay, a matrix that's block tridiagonal is going to have a diagonal, and it's going to have one off diagonal and one off diagonal, and everything else is 0. That's the form of a block tridiagonal matrix. And so each diagonal element is connected to the other diagonal element by one off diagonal element. I mean, this is the kind of Hamiltonian we've been doing the whole time. There's going to be, each row has 3 elements. One couples you to the left, one couples you to the right. This is what we've been doing since 208. And so even though this matrix over here is, infinite, semi-infinite, the indices go from minus infinity to 0. Only two elements couple it to the device, and for that reason, the only thing we need to know from this is what we call the 0, 0 term, and that's our surface green function of that semi-infinite lead. And so this is just using algebra to solve for, I guess, GLD in terms of GDD, and then substituting back into this equation. From row 1, we get this equation that's the only unknown is GDD, and that gives us this form here for GDD. And just by looking at it, we say this is our self-energy due to coupling to the leads. Right? This is our self-energy. The generic form of the self-energy due to coupling to the, in this case, the left lead. And then just to show what that meant, I wrote out these are matrices, so I wrote out what the matrix multiplication meant by just explicitly writing out the indices. And well, these TDL and TLD, these were these guys here, these blocks here, and in this, in those blocks, there's only one element. I is in the device, alpha is in the lead, and there's only one element that couples across. Well, there's the 1, 0 and 0, 1 element, and same down here. So this sum, that's what we said over down here in the lower corner. And so this sum collapses because there's only 2 elements in the sum, 1, 0 and 0, 1. And so the form of your surface green of your self-energy is this, and the only element you need from the inverse of that whole F lead is this 0, 0 element, which is the surface green function. It's the green function of that left lead right at its end, at its surface. And then we went on to show that if you take this form, in our simple model that we've been working with, you get exactly this expression. Or I guess we derived this later. Or we put in this expression for G00 and show that we get this usual expression for the sigma that we had before from chapter 1. And we talked about, really derived what we call the dumb iterative method for calculating the surface green function, where the surface at -1 is going to be the surface at 0 because you've got a semi-infinite number of sites to the left of you. And so you get this this equation here, which you can, turn that into a quadratic equation for G00 in this case, since they're all scalars. But in generally they're not scalars, they're matrices. So you just choose an initial value for G0 here. This is the initial value. Just E minus the site energy, or if they're actually block matrices, E minus that block matrix at 0, 0, plus some small imaginary part, inverted. That's your initial guess, and then you just substitute it into the expression above and just start iterating and just substituting back and iterating until it converges. And it converges relatively quickly. We said it converges roughly linearly. It may converge faster than that, because if you do the expansion, what you're really doing is creating this continued fraction expansion, and continued fraction expansions have very good convergence properties. So this is our dumb iterative method, and it's very easy to code, very robust. First thing you'll ever code. But there are much faster, and the faster method, the sort of method that we use, is this decimation method, where basically you go about, the physicists would say, integrating out every other site and renormalizing your coupling and your site energies and creating a sort of a renormalized chain where you've doubled the lattice constant. You do that, you just keep repeating that. And each time you effectively double the lattice constant until, after n times, your lattice constant is the original 1 times 2 to the n. So after n times, you're coupling 2 to the n lattice constants to the left. And after, very quickly, you're up to like a millimeter, and that coupling is 0. And once the coupling is 0, then you renormalize site energy, you take the inverse of that, and that is your surface green function. So we went through the sort of the algebra of just how you go about just basically just using algebra to get rid of every other term. And then we showed, just explicitly wrote out the, formalized it into exactly how you set up the iteration. And you'll actually see this in our codes if you work with them. And when, these effective off-diagonal couplings were A and B, and basically you just iterate until those off-diagonal couplings go to 0, or something small enough that you ignore. And then your surface green function is just E minus that renormalized site energy. Inverse. And you're done. And so this has exponential convergence, and it was first published in about 1972 by surface scientists who were interested in calculating the surface green function. And we ignored it for about a decade. We thought our dumb iterative algorithm was just fine. And then we, at some point, realized that this was much, much faster. And then so those are basically the iterative methods that we use, the dumb iterative one and the decimation one. So one for quick and dirty You know, if you're just using a small Hamiltonian, nothing too big, then the dumb iterative one is just fine. If you're doing something larger, something more computationally intensive, it turns out that this calculation of the surface green function takes up, you know, a significant, if you like break out where your computation time is going, this calculation is a significant part of it. Because for every energy, you have to recalculate your surface green function. And then if you have, we'll get to talk about this later, hopefully today, if you have like an infinite cross-section, then you have to do it for every transverse K and energy. So you do it a lot. So in the Modespace approach, just like if you were to, you know, the way you first learn about solving for the eigenstate in a quantum well, you say, well, in this well, I know the eigenstates, you know, is e to the plus or minus ikx, and so the solution has to be some linear combination of that, a e to the ikx plus b e to the minus ikx, and you just set a and b to satisfy your boundary conditions, right? I mean, that's the way you first learn how to solve this. And you do the same thing when you're doing waveguides. It's an eigenmode expansion solution for a differential equation. And so what we're doing is we know the general form of our eigen states of our periodic lattice, which we wrote up here. It's this block sum form where the z, this is your propagation factor, and you can just think of it as e to the ika, where in general k could be complex. N is the atom or unit cell index, whatever the periodic index is periodic. It's really formally the unit cell index. And that thing in the ket is a periodic part that gets repeated every unit cell. And so we said if, you know, we're using an sp3 basis, then it would just be some weighted sum of your sp3 orbitals on each atom. That's what we wrote down there. Then you stick that into Schrodinger's equation, that form of psi. You write it out like in the bottom line, and you get this equation with the chi's and the propagation factors for each mode. Multiply through by z, and you get the equation along the top, and we said, okay, that's nice, but it's quadratic in the z, and that's not good. We don't want a quadratic equation with matrices, so you use this trick to turn it into a linear equation by a linear equation for z by doubling the size. Doubling the size of the matrices. And so I just rewrote that same equation in the next line down here. I simply rewrote the equation above it in terms of these, like, I've done nothing here but rewrite it in sort of a matrix vector form. And then to turn it into a generalized eigenvalue form, I added this extra row below, which is just a trivial row, just saying that what's it saying? That negative z chi plus z chi equals 0. That's what that second row says, right? Because this term will give me a negative z chi. This term will just give me the z times the chi, so plus z chi equals 0. I just added the trivial row. But now we have a generalized eigenvalue equation. So if you look at MATLAB, this is exactly the form they discuss. Usually that z is called lambda. So if you just call the eig function in MATLAB and give it two matrices, then it's A and B, then it solves this generalized eigenvalue equation. I can't remember exactly. You know, there's some sign convention. I don't know which one exactly how it sets up, whether it's A plus lambda B, whether it solves that one, or B plus lambda A, or plus or minus. You need to check the MATLAB documentation. But something like this in MATLAB, if you look up the Eig function. And so, you know, all we've done is double this. So I guess if we're thinking of our SP3 basis, then initially these matrices, my D0 and my T's are 4 by 4, right? In my SP3 basis. If I think of one atom per unit cell, right? One atom per unit cell, think of my linear chain, then those would be 4 by 4 matrices. And so what I have to sort of compromise is I got to turn them into 8 by 8 matrices to solve this. And so once I've turned them into those 8 by 8 matrices, then I call my Eig function in MATLAB. Or in general, if you're not doing it in MATLAB, your Laplace function, I think I wrote it down here, ZEGV or something, the generalized eigenvalue solver in Laplace. And solve it, and what you get out of this is Z, right? You get the value for Z, that's your generalized eigenvalue, your propagation factor. And you get this eigenfunction over here on the right. Here's the eigenfunction that you're going to get. And it's sort of, a redundant amount of information in that eigenfunction because you only need chi. So basically you get it and you throw away the bottom half of the eigenfunction. And so that's as far as we got last time. And now we'll discuss, once you get that eigenfunction, what do you do with it? Okay, so if you notice, this is different, rather different than your usual, what we were doing in 208. This is, in 208, we were looking at, copy and paste this. Okay, so in 208, we were always looking at this h of k minus e psi equals 0. Right, that was, when we had a periodic crystal, that was what we were solving, and so k was an input. Right, k was an input. You'd choose a k in your Brillouin zone. You'd construct h of k, and then you would solve the eigen. And so in our S, say you have one atom, 4 orbitals, that you would get, if you do this numerically, you choose, let's see, what am I plotting? E. So this is E, and this is K. So you choose a K, and then for each K, you're going to get 4 solutions, right? And then you just move along in K, and then you string these all together, and you get, your 4 bands, some 4 bands. That's a terrible drawing, right? You tie all these points together, and you get your 4 bands that come from these systems. So the K is an input, E of K is the output. All right, this is what you were doing in 208. Now, if you look at this generalized eigenfunction equation, and let's just continue to think of 1D to keep this simple. There's no K there. Right? There's no K here. And E is an input. E is not an output. E is an input. So now, for our generalized eigenvalue, equation, E is an input. And Z equals e to the I Ka is our output, which means that taking the log of that, K is the output. And so what that means is that for this, for our generalized eigenvalue solver, you choose an E. So I've chosen E, and I'm going to get, and now usually what people do is you have real K on one side of the axis and imaginary K on the other. You choose an E, and you're going to get well, actually you're going to get, we have SP3, you're going to get 8 Ks. And they're going to be they're going to come in pairs, and then the pairs represent forward moving and backward moving velocities. They come in pairs, and the pairs represent one state moving to the left and one state moving to the right. So you're going to get, so for sp3, 1 atom per unit cell, you're going to get 8 Ks, and they come in pairs, and the pairs represent plus or minus velocity, moving to the right or moving to the left. We will need to sort these by which way they're moving, depending on which lead you're looking at. So we have to sort these modes. So we need to sort the modes into left and right moving. Okay, and so the way you do this is that if you think of let's first think about the band structure of some typical so a direct gap, simple model band structure, you'd have a conduction band, and you'd have your 3 valence bands. Right, forget spin orbit and all that stuff. 3 valence bands. Okay, that'd be a very simple sort of model band structure, right? In our sp3 basis. And this axis is energy. This is K. And we said we're just going to, E is the input. And so, what happens when I choose an E in the middle of the band gap? So, okay, we're going to input an E. There's a perfectly good E. Now what's going to happen?
Imaginary K.
All of the solutions will be imaginary Ks because they're all exponentially growing or decaying solutions in there. How about if I choose an energy up here?
Real plus minus.
And I'm always going to get 8 solutions. Right? I'm always going to get 8 solutions. So I'll get 1 pair that are real K, and the other 6 pair which are imaginary K. There's only 1 real band up there, right? And so I will get this solution, I will get this solution, and I will get some imaginary bands that are coming off of here to give me the other 6 solutions, but they'll be imaginary. They'll be evanescently decaying, as if I was tunneling through this band, tunneling through one of the valence bands. Right? I can always tunnel through through another band. That's tunneling. You don't think of it that way, but if I'm, when we're in the band gap, you say you're tunneling through, what band are you tunneling through? In a one-band model, you'd be tunneling through the conduction band. Well, now if I'm at at an energy way up here, then I can also be tunneling through an evanescent valence band, right? So you always get 8, no matter where you are. Most of the solutions will always be these evanescent, exponentially decaying or growing solutions. And so you're going to get your 8 solutions, and then the question is, okay, so we need to sort them into right and left moving. So let's talk about how to do this. But first, then we just write down a few things. So in this case, you get 4 states going right, 4 states going left, and for the chi's, you only keep, for the chi that you get, you just keep the top half. And normalize so that you have chi m over chi m. Because MATLAB may normalize, but they'd normalize the whole thing that's coming out of the eigenfunction solver. You don't want the whole thing. You just want chi, not chi z chi. Okay, so let's talk about sorting. So how do we sort these things? Okay, there's a couple of easy cases, which, you can picture this as an if-then-else type algorithm. So first, if, I'll just write it down. If Zm, if the magnitude of Zm, since it's a complex, right? It's like e to the I kappa A, where kappa is complex. So if the magnitude is less than 1, and numerically, you can't just say less than 1 when you're dealing with real or double precision, right? You got to be a little more careful than that. So by trial and error on the machines we were using at the time, we found that this criteria worked pretty well. It had enough precision. So less than 1, specifically, we would say less than 1 minus 10 to the minus 8th. You understand why I'm doing that?
I mean, why does 10 to the power 8 factor comes?
It's just something that gives you a number less than 1. But it also sort of was based on what kind of numerical precision we found by trial and error. That if it's closer to the 1 than that, then you just start, you don't know whether it's really less than 1 or whether it's just numerical noise.
Okay. You mean just carefully setting less than 1 with the noise margin?
Yeah, exactly, with numerical noise. You can't just say less than 1 because there's numerical noise and it will give you a false result.
Right.
Because we have to consider the case when it's equal to 1. But again, you're using real or double precision. What exactly does equal to 1 mean? It's within some numerical tolerance because it's all being done numerically. So we found that this worked well when and we did everything with at the time in double precision, double complex. So this kind of worked okay.
But shouldn't that number 10 to the power minus 8 should be machine dependent?
What's that?
Shouldn't
Yeah, it probably is. So you want to know what machines we were using? Well, I mean, I don't know. It was a 64-bit machine with usual, Fortran definition of double precision. I mean, double, and double complex. So I don't know how machine dependent that is. I guess it is to some.
But like different compilers, different precision a little bit different. I don't know whether there is a.
I mean, given the same number of bits, you would think.
Yeah, actually it will depend on the mantissa and the range of the.
Yeah. If you're using 64-bit machine, I don't know.
It's fair enough.
We were all doing this back on a SGI. They called it a supercomputer back in the 90s. Wouldn't be so super anymore, but the precision was still a 64-bit machine. Everything declared with double precision or double complex. Anyhow, so this worked. Worked for us numerically to let us know that the magnitude of z was less than 1. Really, we're just asking, is the magnitude of z less than 1? But we have to do this in a way that works numerically. If it's less than 1, then it means, what does that mean? You've got if you break k up into a real and imaginary part, you've got e to the I k, the real part, a, and the magnitude of that is 1. And the imaginary part is e to the negative k imaginary a, right? So if the imaginary part is positive, then this second term is less than 1. If the imaginary part is positive, and this thing represents something that's decaying as you move to the right. So if this is true, then you have you're decaying to the right. So you say that's a positive velocity. You throw that into the positive velocity group, right? I mean, the form of our wave function was chi m z m. So this whole thing is zm, right? This whole thing I wrote up there is z sub m. Chi m zm raised to the n, where the n is the unit cell index. So as that index is increasing, this thing is decaying. So we're moving to the right. And every time you move to the right, you pick up a phase factor. And then, else, if the other zm is greater than 1.0 minus 10 minus 8, then it's decaying to the left. It's going to get smaller as you go on the negative. It's just the opposite of what we wrote. I mean, the imaginary part is negative. It's decaying to the left, so that you throw that into the negative bin. Those are the two easy ones. Now, if it's neither that one or the other, there's a third one that, well, it's equal to 1, and then you got to figure out which way it's moving. else if, or just else, right? So it's neither less than 1 or greater than 1. I just need else. That means it's equal to 1, and I got to deal with it. So else it's equal to 1. Z, the magnitude, is equal to 1. And then you need to calculate the sign of the velocity using the eigenstate itself. There's no good way of doing that, because you can't just look at the sign of k, because we're dealing with real band structure in general, right? You can have stuff like this, and so even though k is positive throughout of all here, right, the velocity is negative here, it's positive over here. You can't just look at the sign of k to figure out which way the state is moving. But you can get it from looking at the wave function itself, and in sort of the same way that when you calculate current, the first thing you learn is like h bar over 2im psi star grad psi minus grad psi star psi. Yeah, we have class today. We'll have a discussion section Friday. Right, and this expression will give you the sign of the current, right? What I just wrote down. So buried in the wave function itself, you can extract the sign of the current. And so we're only interested in the sign, not the magnitude or anything else. So the velocity of mode m is proportional to negative 2 imaginary chi, because these are column vectors, chi m dagger t 01 chi m z m. And since you have all that numerically, you've got your coupling matrix elements, you've got your propagation factor and your chi, you just evaluate that, and you just look at the sign. So if this is greater than 0, then it's positive, and less than 0, then it's negative. I don't care about the magnitude, I just need to get the sign so I can sort these into positive and negative moving states. And if you look over here at this expression that we wrote over here, you can see that I don't know, is that going to be, that's like something minus its complex conjugate. So that's going to, and then you divide by I. So that's like the imaginary part, right? This is like an imaginary of what's in parentheses, right? And that grad, when you discretize it, would become like the T that couples, the grad becomes a T when you discretize it. Okay, so that's what we implemented, and that worked pretty well. So now we have the size, and we've sorted them into two groups, left moving and right moving. And so now we're ready to solve for G what we really want for our surface green function. We're ready to solve for our surface green function. Okay, so the equation looks identical to what we wrote down for our simple tight 1D tight binding chain, except we just turn everything into matrices. So I have negative, these would be in this example, we've been doing 4 by 4 matrices, negative t, 0, comma, negative 1, g minus 1, comma, 0, plus E times the identity matrix minus D. That would be your diagonal block. I'm replacing it. Ordinarily, we've been writing that as epsilon, but now it's your 4 by 4 diagonal block acting on G00 is equal to your identity matrix, your 4 by 4 identity matrix. Okay, so this guy, G negative 1, 0, physically, how do you interpret what that thing is? If I ask you physically, what's G negative 1, 0? What is that thing?
One atom left in the surface.
But what does it represent? And well, first of all, what does the green function represent?
Coupling to the lead.
I want something more general than that. See, impulse response to the system. And so, if G negative 1, 0 is an impulse response, tell me exactly where I'm hitting it and where I'm measuring the response.
Hitting -1 and measuring at 0.
Now, the weird thing about green function indices and all this, you hit it on the outside index and you measure, so it moves just the opposite of everything you sort of intuitively think about matrices. So in all these, the way these green function indices work, and this is all throughout your many-body physics, you hit it on the outside index and the response is measured on the inside index. So we're hitting it at 0 at the surface and measuring the response at negative 1. One site in. And so that response, right, if I hit it, that response is carried by the leftward moving eigenmode. That response has got to be carried, transmitted by the leftward moving eigenmodes. So what we did before in our little toy single band model, we wrote down that G minus 1, 0 was equal to E to the I Ka G 0, 0. And now in our new notation, we say that our leftward moving Z is e to the minus IKA, and G minus 1, this is going to clarify a question that you may be asking yourself right now. That's why it's e to the IKA. So G minus 1, 0 is ZL to the negative 1, because I'm moving backwards one site, times G00, 0. Right? The way we define these Z's is Z to the N, but N is going to the left, is decreasing. And so the propagation factor is e to the minus IKA, but I take the inverse because I'm going to the left. Right? We defined all these eigenmodes as just Z to the N times chi. Well, N is now negative 1. So now in the multiband model, we take G00 and we project it onto each left moving mode. So it's really going to be a basis transformation. G00 is written in our localized atomic orbital basis. It's going to be a linear combination of sp3. But now we're going to have to write it as a linear combination of the 4 leftward moving eigenmodes. There's 4 of each, 4 to 4, so it's a unitary transformation. So we do a basis change into the 4 leftward moving eigenmodes, and there's one more subtlety here. So we can write the 4 atomic orbitals as a linear combination of the 4 modes. However, the subtlety is that these modes were not the result of a Hermitian eigenvalue equation. We did not solve a Hermitian eigenvalue equation to get these modes. We solved this generalized eigenvalue equation to get these chi's, which means that the chi's are not necessarily orthogonal. Right? Only if you solve a Hermitian eigenvalue equation are you sure that you'll get an orthogonal set of eigenvalues. So your chi's come from this generalized eigenvalue equation. Which means that they're not necessarily orthogonal. And so to deal with this, and we'll come back, we'll bump into this later on at some point when we deal with a non-orthogonal basis set, which we haven't had to think about so far. Formally, whenever you have a non-orthogonal basis set, you define a bi-orthogonal mode basis. And this is just something that we do for formal manipulation. I don't think we ever need to know what this bi-orthogonal set is. So it's defined such, we know the chi's, right? The chi's are given. They're whatever we got out of our generalized eigenvalue solver. But you define the bi-orthogonal set are these z's, and they're defined such that this is true. So if for Zm and chi m, you take the inner product and you get 1. If m prime is not equal to m, you get 0. But the z's don't have to be one of the chi's. The z's do not have to be contained in the set of chi's. In fact, in general, if there's a non-orthogonal basis, they're not. So this would be, you've got the set of chi's, and you've got the set of z's, and this is your what they call a bi-orthogonal. So the z's are also a basis, and they would be your bi-orthogonal basis. Your chi's are a basis, and they're defined so that what I just wrote down is true. Okay, so let's see. Let's do this projection now. So now we'll do this projection. So, and for the alpha I are going to indicate my atomic orbital basis, my atomic orbitals that we've been using. And this bioorthogonal stuff is going to confuse everybody. It took me years to figure out that this was the correct way to do it, but if you've never seen it before, it's kind of confusing. What we need is to relate our G -1, 0 to G 0, 0, like we did before. Before it was, we were dealing with scalars and it was trivial, right? And we want to do that so that we can close, just like what we did before, close this equation and have something that we can solve for just G 0, 0. So we have to, use everything we've done to relate G -1, 0 to G 0, 0. And so, in terms of my orbitals, I guess alpha I would be my atomic orbitals. My G -1, 0 I can write as alpha I -1, so that'd be my orbital and my site. And G, so you can think of taking the matrix elements of G, and what have I got over here? Alpha J and 0. Right, so I'm going from site 0 to -1, from alpha J to alpha I, two different orbitals. So these are just a fun, this is what I mean by G sub alpha I -1 alpha J 0. From site 0 to -1, from orbital alpha J to orbital alpha I. Right? That's what we mean. And that's equal to sum over my modes, alpha I -1 chi m -1 Zm inverse times Zm comma 0 G and then alpha J 0. And if these Z's, you can, in your mind, you can just think of replacing that Z there with a chi m. And so what this means physically is I inject, as usual, right? I inject into 0 and orbital alpha J, and then I see the response again at 0, but in mode M. This would be the green function that takes, I inject into orbital alpha J, and I'm getting the response in mode M. And then it propagates, once it's in mode M, it propagates with my propagation factor, because I'm now in a mode, and I know how modes propagate, back to site -1, still in mode M, because once I'm in a mode, I stay in a mode forever. It's an eigenmode. And all I'm going to do is pick up this a z to the n for each site I propagate back, and then I project back into my orbitals at site -1. And so, if you're thinking, don't worry about the z, you can just think of this as chi m here. We'll come back to this in a second. So I injected 0 alpha J, I find the response at 0 chi m, and then I propagate back one site with my propagation factor and project it back onto the orbitals at site -1. Now the thing is, I don't know what this green function is that goes from alpha J to Zm, so I got to put in another set of complete states. right? Is you just keep, this is what we said in 208, you keep putting in complete set of states until you get something. So this is sum M, sum P, alpha I, -1, chi M, -1, Zm inverse, and then this Zm0. Here's my new set of complete states. Alpha P 0, alpha P 0, G alpha J 0. And so now this thing on the right is the surface green function. It's in my equation. That's just my normal surface green function in my atomic orbital basis at site 0. That's my standard. I'm sorry, that should be an alpha. This is supposed to be, I don't know, alpha P. It's supposed to be a P here. So I just threw in another complete set of states, sum over alpha P. And so now we have to, I mean, that's still not very, if you look at that, you go, wow, that's not very enlightening. But now the way to make sense of it is you write it out in terms of a matrix equation. And so what we've got is that the matrix, my 4x4 matrix, G -1, 0, is equal to the matrix of chi's, so chi 1, chi 2, and these are the chi's that you've got from your generalized eigenvalue, chi 3, solver. Just stick them together into a matrix. There's one matrix, right? That's a 4x4 matrix. It's each chi is 4. Has 4 elements. Times a diagonal matrix of my propagation factors. So Z1 inverse, Z2 inverse, Z3 inverse, Z4 inverse. Times the matrix of the Z's. So Z1, Z2, Z3, Z4. Times your original G00. So that's the transformation we're talking about that relates G-1, 0 to G00. So what the heck is all this? So this we just referred to as the matrix chi left is your matrix of leftward moving chi's. This we simply refer to as the matrix ZL inverse, your diagonal matrix of propagation factors. And this thing is simply the way we defined it, and this is why you never need to know what these Z's are, chi L inverse. That's what that matrix is. You never, if you go back and look at the way we define the Z's, if you multiply the chi matrix times that Z matrix, because you get a Kronecker delta if when chi1 hits Z1 but 0 for any other row, you'll see you generate the identity matrix. So that Z matrix is chi L inverse, right? Because when chi1 hits Z1, I get 1. If it hits Z2, Z3, or Z4, I get 0. Same one, when chi2 hits Z2, I get 1. If it hits Z1, Z3, or Z4, I get 0. Because the way we defined it, right, was Zm prime chi m is this Kronecker delta m prime m. And so that Z matrix is simply chi L inverse, the inverse of the chi matrix. So you get the chi matrix, you take your 4 leftward moving chi's, you stack them up, column vectors, create your matrix, take the inverse, you have this diagonal matrix of your propagation factors, you just do that matrix multiplication, and you've related G negative 1, 0 to G 0, 0 in this mode space approach. Okay? You do your generalized eigen, so you know, in the way you're doing a negative solution, you choose your energy, you do your your generalized eigenvalue solution, you get your 8 modes, you sort them. For the left lead, which is what we've been doing, you take your leftward moving modes, which are moving, the ones that are actually moving away from the device, because you want to find out what G negative 1, 0 is in terms of G 0, 0. And they're the ones that are carrying the response. And then you just solve, and then you just, this is the relationship. So once you have this, now you have a closed set of equations. So formally, in terms of the way we've defined this, we can say that using a more compact notation, that the matrix G negative 1, 0 is just chi left, the matrix chi left, the matrix Z L inverse, chi left inverse, and this is sort of a more revealing way of writing it actually, G 0, 0. And if you look at this, here, it looks like what you first learned for a basis transformation. You got a diagonal matrix times, you know, A on one side, A inverse on the other. And that's exactly the form of a basis transformation. So you can think of, you're transforming the propagation factors from the mode space basis into the localized orbital basis. This is a classic form of a basis transformation. And so once you've done that, then you've closed your system of equations. And so the surface green function on your left, for your left lead, is E times the identity minus D minus T 0 minus 1 chi left Z inverse, chi left inverse, and the whole thing inverted. The whole thing inverted. Whole thing inverted. E minus D minus is T chi Z inverse chi inverse, the whole thing inverted. And there's your surface green function. Calculated from a Modespace approach. And we can go through the same thing on the right side. So on the right side, you're going to have G. Let me just call it 0, 0 again. For the right lead, the surface green function for the right lead is going to be E I minus D minus. So my again, for my right lead, I'm saying it starts at 0 and goes to infinity. 0, 1. Matrix chi. This would be your right moving chi's. Your right moving propagation factors. But notice they're not inverted now because you're moving to the right. Right? To truncate so for the right lead, the lead over here, I got 0, 1. I'd be looking at the response going from here to here, and that's just Z, not Z inverse, right? Because now I would need to relate G. Let's see, I hit it 1 comma 0. I need to relate that to G 0, 0. So my propagation factor would just be Z instead of Z inverse. But I'm hitting it at 0 and asking for the response one node to the right. Yep. Anyway, so Z chi R and then chi R inverse, and then the whole thing inverted. Those would be my surface green functions in the Modespace approach. I guess it would have been better just to write down the starting equation for the right-hand side was EI minus D G 0, 0 minus T 0, comma 1 G 1, comma 0. Right, that's the equation I'll be starting with on the right-hand side for the right-hand lead. That's a good place to take a break. Let's take a break.